Hello, y'all. Welcome to lesson 94 of the DP Chemistry curriculum. Today, we're going over reactivity 3.1.1. We will discuss Bronsted-Lowry acids, how they are proton donors, and how Bronsted-Lowry bases are proton acceptors. We will deduce the Bronsted-Lowry acid and base in a reaction. So with that said, let's just go over the general definition of Bronsted-Lowry acids and bases. And what are acid and bases anyways? When we talk about acids and bases, we're actually talking about proton transfer reactions. We call it proton transfer because acids, specifically with the Bronsted-Lowry definition, donate a hydrogen ion, a hydrogen plus one ion, which if we look at a hydrogen plus one ion, that is just a proton. We can deduce that from the Bohr model, where we have a single proton in the nucleus and one electron in the first energy level. When we then lose that electron to become a plus one ion, we are left with only the proton. That is hydrogen plus. This is why acids are generally referred to as proton donors. So just to clean up that definition a little bit, a Bronsted-Lowry acid donates a proton. A Bronsted-Lowry base accepts a proton. Also, from this point forward, I'll just start using BL so I do not have to rewrite Bronsted-Lowry a million times. So when we put a Bronsted-Lowry acid in solution, the hydrogen converts to hydronium in a reaction with water. So we'll see what that looks like. H plus aqueous plus H2O, our water liquid, reacts to form H3O plus aqueous. You'll actually notice because this H plus is attaching to the water, our H plus is our acid and our water is actually acting as a Bronsted-Lowry base. Oddly enough, that is the process by which we produce hydronium. When we look at more familiar acids, such as dissolving, let's say, hydrochloric acid, HCl, in water, we can now explore the process using these definitions. So HCl, which will originally be in its gaseous form, will react with water in its liquid form, and we will produce H3O plus aqueous, as well as our chloride ions, aqueous. You'll notice the hydrogen from HCl transfers to the water, and therefore this is our Bronsted-Lowry acid, and our water is our Bronsted-Lowry base. So this is what it looks like to donate a hydrogen in solution. We can actually look at it the other way with bases. So now we'll say we dissolve ammonia, NH3, in water. So now we have ammonia, also a gas, plus H2O, reacts to form, and this would produce ammonium, NH4 plus hydroxide. Both of these will be aqueous. In this scenario, water is the one donating the hydrogen ion or donating the proton, and water is our Bronsted-Lowry acid, and ammonia is our Bronsted-Lowry base. The important thing about all bases is that all Bronsted-Lowry bases, and for most bases that you ever interact with, they must have a lone pair of electrons to accept the proton. So what you'll notice is that in our first example, the oxygen has two lone pairs that the hydrogen will append to. And in our second example, nitrogen within ammonia has one lone pair that then gets the hydrogen appended to it. So we must have that lone pair to accept the hydrogen. It is where the hydrogen will form that bond. Now, before we finish acids and bases or this intersection, we are going to cover the three types of acids as well as the three most common groupings of bases. So, three types of acids. These aren't the only acids, but the three types that you'll experience throughout the DP curriculum. The first type are binary acids. Binary acids, like the name suggests, are just usually two things. It is a halide plus a hydrogen. So common examples are hydrofluoric acid, HF, hydrochloric acid, HCl, hydrobromic acid, HBr, and hydroiodic acid, HI. So any of our halides plus a hydrogen just becomes hydro blank ic acid. So those are our binary acids. For the second grouping, we have what's called our oxyacids. These are derived from polyatomics. So you must know your general polyatomics as well as their relative charges. Nitric acid. Nitrate is NO3 minus, and that 1 minus will append to 1 plus to form HNO3. You could also have carbonic acid. Carbonic acid comes from carbonate, CO3, and normally it's 2 minus, meaning that we have two hydrogens to create that acid. Sulfuric acid comes from sulfate, which is SO4, 2 minus, but because it's 2 minus, we'll have two hydrogens. Or phosphoric acid, which comes from phosphate. Phosphoric acid is PO4, and normally there's 3 minus, so we have three hydrogens, H3PO4. You can apply this to any of the negative polyatomic ions. There are far more. All right, the third type of acids we'll look at are organic acids. Organic acids generally have the carboxyl group. Carboxyl group, and that is the group that has COOH. Specifically, it's a carbon double bond to an oxygen, single bonded to an oxygen, which is bonded to a hydrogen in turn, and that is bonded to some hydrocarbon chain. Now, organic acids, some common examples that we generally see are something like ethanoic acid, CH3COOH, or possibly something such as benzoic, or not even benzoic acid, butanoic acid. Or no, let's do benzoic acid. Coming from benzene, C6H5COOH. So these are some common acids that we will see. And now, before we move on to the bases, let's just discuss the three types of acids. Also, something you may have noticed is that each acid contains a hydrogen. That's the proton that leaves it. And in these, it's these last protons. But an important note is that not all hydrogen-containing compounds, are acids. We'll learn a little bit later in this section what makes it an acid and why that hydrogen is willing to leave or be donated, but we can't just make the blanket assumption that a hydrogen makes something an acid. Generally, when it's written, you'll see it either at the front for almost all acids or at the back for specifically organic acids. Furthermore, based on that number of hydrogen, We could have monoprotic, meaning one proton donated or one hydrogen. We could have diprotic, which would be two hydrogens. We could have triprotic, which could have three hydrogens. If we look at our examples from above, just looking at our oxyacids, nitric acid would be monoprotic as it only has one hydrogen to give. Carbonic and sulfuric would be diprotic as they both have two hydrogens to give. And phosphoric would be triprotic, having three hydrogens to give. All right, the last thing we're going to cover now is finally our common bases. And we'll go pretty quickly through these. For our common bases, these, like we mentioned before, they have a lone pair to accept protons or H plus ions. So usually most oxides and hydroxides. Examples include calcium oxide, maybe copper oxide, copper 2 oxide in this case, or sodium hydroxide, or maybe calcium hydroxide. So these would all be very common bases. Furthermore, in addition to oxides and hydroxides, carbonates and bicarbonates. Bicarbonate is just a fancy way of saying hydrogen carbonate. Some good examples of this might be sodium bicarbonate, NaHCO3, which is baking soda, or possibly just sodium carbonate on its own. And you'll notice we call this carbonate and this hydrogen carbonate because it has hydrogen in front, another name for it being bicarbonate. The last group of basic acids we'll cover are ammonia or amines or amides. So these are going to contain nitrogen, fulfilling a role similar to oxygen in these other ones. And being ammonia, we'll have NH3, or we might have something like ethanamine, which would be CH3, CH2, and H2. So these are all common bases. Now, in these bases, generally the oxygen is where we will accept the hydrogen. Furthermore, same for the carbonates and bicarbonates. However, in ammonia, amines, and amides, the lone pair belongs to the nitrogen in these groups. So hopefully this helps you understand the intro to acids and bases, and have a great day.